Okay, everyone, so let's take your seats and get things started. So today we're very excited to get Professor Wanliang from Syracuse University to join us. Professor Shan is actually an expert in cross-sectional research across the solid-state mechanics, material science, thermal engineering for soft robotics and dynamic applications. Actually, for our discussions at lunch, looks like he's also looking for some aerospace applications. Dr. Shan's work has been well recognized by different government agencies, especially recently has been recommended for the prestigious NSF Early Technique Korea Award, which is basically a great honor for young scientists. And also, he has been involved in different innovation and also entrepreneurship efforts, also by NSF, Partnership for Innovation, as well as ITOR. He also served as associate editor for IEEE robotics and automation matters, so it's a prestigious journal. It's in the section of soft robotics. So we look forward to his exciting talk. Thank you.
All right. Thank you. Thank you. So thank you, Jifeng, for the nice introduction and also for the invitation to give this seminar. I also want to thank you all for coming. I know this is a Friday afternoon, 3 p.m., 3:30, right, actually? Yeah, 3 or 3:30. It's late, so I'll try to entertain you, hopefully. Another thing is I want to say, I have enjoyed my visit so far. This is a beautiful spring day. I thank the students and the college the faculty members for the tour and also the conversation together. I want to thank you for that. On a similar note, let me see here. Okay, on a similar note, I want to see up front that actually my group members have contributed a lot to this seminar. These include students, undergrad students, grad students, and also postdocs. In particular, I have Dr. Guangchou Wang, my postdoc here. He actually is an alumnus of Dartmouth School of Engineering, working with Professor Zi Chen. He graduated from here back in 2020. And he has done fantastic work, which I will share towards the end of this seminar. I want to thank Dartmouth for the good training he has received from here. Okay, this is a research topic. So when we talk about robotic modulation, right, the first thing coming to mind might be these gigantic ones that can be found at the manufacturing lines. The whole field of modern robotics actually all started back in the 1950s with a robotic arm by George Devil. Over the last 70 years or so, the field of robotics actually have grown into other periphery areas such as biomedical devices and wearable devices. So here I have a few examples, including this robotic needle for suturing applications, and also this drug illuminant for heart disease treatment, as well as this exoskeleton for human-machine assistance. We can see that actually from the left to the right, there are more and more machine-environment interaction involved. Among these, most importantly, there are more and more human-machine interactions. This is a trend we were seeing, actually. So human safety, human comfort, and also environment adaptability is the key for robotic design right now. Indeed, because of the more and more human-machine environment interactions, we have seen this surge of soft robotics research in the last 10 years or so, last decade or so. We can see that actually from left to right, I have 3 examples here. The first one is a crawling robot made of entirely elastomers. This middle one is a soft gripper for food packaging by Soft Robotics Inc. This is a startup company coming out of Harvard, I believe. And here there is also a soft robotic glove for rehabilitation purpose. Compared with traditional robotics, actually, soft robotics has these advantages such as better adaptability to unexpected environments, safer human-machine interactions, but coming with also there are challenges such as being less precise, harder to control due to the non-trivial dynamic modeling part. There are also less commercially available sensors, actuators. All these challenges actually they mean opportunities for us as researchers. If we look at traditional robots and our human body, we can see that actually the two use materials sitting at the opposite end of this modulus spectrum. Traditional robotics use hard materials, metals, silicon, and also hard plastics, whereas our human body mostly consists of tissues and organs, mostly soft, squishy stuff. So, but if we examine clearly, more carefully, we say that actually our human body are not entirely soft. Actually, we are hybrid. We also have rigid materials such as bones and cartilages, and also muscle. Our muscle actually can stiffen or relax depending on what kind of job we are trying to do. So in a similar way, we will expect actually small materials with tunable stiffness that can also be used in many soft robotics mechanisms to get the best of these two worlds, right? When it's rigid, it's rigid. When it's soft, and you can switch between the two to design robotic system for better human-machine environment interactions. With that, this is the research theme on my group. We are focused on smart, hybrid, active, and nature-inspired materials, mechanics, and machines. So I want to integrate my background in materials engineering and solid mechanics to impact critical application domains such as soft robotics, biomedical devices, and also wearable devices. Along this theme, we have, over the years, we have done many projects. Here, I show this. This is a small material product, which I don't have time to detail about today. But you see the structure there. We also look at wire buckling mechanics. This is for the design of robotic needles, potentially. And also more recently, we are looking at curling robots. This one is based on extreme memory alloy wires. And this one is, more recent, is based on tunable friction. Today, actually, I'm going to not talk about those in detail, but instead focus on adhesion mechanics and soft grippers based on adhesion mechanics. With that, pretty much, we covered the background and motivation part. This is the outline of the talk. So next, we're going to look at existing compliant gripping approaches. This include existing approaches by other groups, and also one recent study by my group. We're going to comment on their common limitations, and then propose new approaches based on this subsurface stiffness modulation. We call it SSM, or subsurface pressure modulation, SPM. And we're going to do outlook and future work for compliant manipulation after covering these two, and use an example such as shell adhesion mechanics to indicate what exactly we're going to do for future on this topic. In the end, I'm going to conclude and provide acknowledgements. Well, software gripper, right? I showed a couple already. The one by Soft Robotics Inc. Here there are more examples. This first one is a multi-finger soft gripper. And each finger actually is made of a bilayer of elastomers with different stiffness. And they have chambers that you can inflate. When that happens, the soft layer is going to extend more, and the rigid material will extend less, and you're going to generate this bending motion, and collectively, with multiple fingers, you can grasp objects. You can release when you remove the pressure. This approach is elephant trunk mimic soft gripper. You can see that actually this one is based on incompressible liquids. Because they use the liquid, they can do more heavy-duty stuff. This is actually a piece of a rock here being lifted by this elephant trunk mimic soft gripper. There are also other approaches based on pneumatics. This one uses particle jamming or granular jamming. This is actually a balloon, rubber balloon, and they have ground coffee inside. When you don't take the air out of this balloon, this composite structure can adapt to whatever shape and try to pick up all sorts of objects. And then you can take air out. The ship will be locked, and you can pick this out. Actually, there has been a company built. The name is Empire Robotics. They started back in 2013, 2014, roughly, and they filed for bankruptcy, actually due to fatigue issue. Turns out there is fatigue when you try to do this grasping, and this rubber, thin layer of rubber balloon here is not durable enough for pick-and-place operation in a factory setting. Last example here actually combines multiple approaches with particle jamming and also evacuation pump, etc., such that they can do multiple vanes actually in the structure. These are based on pneumatic approach. There's another approach called it's called electro adhesion. So this one actually, I have a recent study back in 2016, 7 years ago. This is the two-finger soft gripper. With each finger actually is a multi-layer structure. You have a middle layer pre-stretched during fabrication, and you can adapt. Then you can attach another 2 layers on the top and on the bottom. Because of the initial stretch, when you release the structure, actually the finger will be naturally in this curled geometry. When you apply high voltage, like 1,000 volts, right, this curled geometry will straighten again because of the strong electric field across this thin film here. The film there is dielectric elastomer, right? So they can stretch and you can get close to objects and you can pick them up. They have shown actually this gripper can pick up like an envelope, right, very thin object, or this 3D printed parts, cylindrical shape, or this even peeled fruit here. They can do all sorts of things. The drawback I would see is they need high voltage, like 1,000 voltage to do this, and they tend to have trouble when the environment is humid. There's also application of electro adhesion in the fabrics domain. So this is another startup company called Grabit. I visited that company actually back in 2018 in Silicon Valley. That time they were working on this project. They also have another project with Nike. So the sneaker we wear, right? Today I don't wear sneakers, but when I play basketball or run, or do my running, so I wear sneakers. They were using a machine based on electro adhesion approach to optimize the sneaker manufacturing. Later on, actually, in the pandemic, this company actually right now get bought actually by Nike. They become a unit of Nike right now. Yet another approach is based on dry adhesion. The main source of inspiration actually comes from gecko. So over the last few decades, actually, researchers have really understand well how gecko's adhesion work. Their feet actually have multi-hierarchical structures, all the way from nanoscale to macro scale. So Professor Manning City's group right now at Max Planck Institute, and also Professor Alfred Crosby group, not far from here at UMass, they have been doing a lot of work along these topics, and they were able to show that actually they can do directional adhesion based on gecko-inspired approach. My colleague Kevin Turner at Payne actually they took a slightly different approach. They argue that actually if I start with otherwise homogeneous pillar, elastomer pillar, and I insert a rigid core inside this pillar, I will be able to enhance the dry adhesion. They did experiments. Here you can see here the T, the thickness between the bottom of this rigid layer and the interface. When they keep the R the constant and reduce T, which means you're moving from the right to the left in this plot, the dry adhesion will go up. And there will be a maximum switch actually from edge crack to center crack right at this critical value. They show that actually the reason for that switch is because of the stress distribution manipulation. So when you have a homogeneous elastomer pillar, there will be stress concentration right at the edge. When you insert a rigid core, however, this singularity on the edge will be suppressed, and the stress will be much higher in the central region. When you push this thickness to be thinner and thinner, this central region will become dominant. So instead of having edge crack, in this case, you're going to have center crack when the T is small enough. That's predicted both by fundamental simulation and also by experiments. There are also multiple approaches developed for soft grippers. This one actually they are combining pneumatic approach with array of micro fillers. This is done by Manning group again. And yet another approach, this one they also have array of pillars. but then they have this membrane, right? The aerial pillars are attached to the membrane. They have this chamber here. They can modulate the pressure such that they can increase radiation to increase contact, actually, to increase radiation. And they demonstrate that actually this scraper works across all sorts of objects with various shapes and weights. My group also did something on a similar line. We proposed a multi-finger soft scraper. So we literally using small materials with tunable stiffness, like artificial muscle, right? On the side of the wall as a ligaments. And each finger actually here, as you can see, you have 3 ligaments here made of small material. And also they have 3 phalanges and 2 joints. The joints are softer. Then in the middle, you have a chamber, and you can inflate such that actually when you activate the ligaments, selective activate ligaments, you will get a bending moment out of this. Then when you try to selectively activate this set of ligaments for 3 fingers, you will be able to generate this closing motion, or you can activate the opposite set of ligaments. You can get opening manipulation. This way you can do dropping of objects. Yet another combination is you do these 2 sets, you can generate the twisting. By the way, twisting has not been demonstrated for a long time, since back in the 90s. So for the small material, we use CPB, or conductive propylene-based elastomer. For this elastomer, we start with some copolymer elastomer based on polypropylene, and then we can add structural carbon black into it. We can laminate this pellet form into thin films, and then use laser patterning to get whatever shape we want. Here is a demonstration that we can activate this U-shaped strip by running current through it, and here is the activation results. You can see that actually roughly within 10 seconds, we are able to soften the material completely using tens of volts. Now, back to this ligaments, right? Soft scrapers using this small material ligaments, we actually demonstrate manipulation of this soft scraper, all sorts of objects using this soft scraper. Here is a ping pong ball. There's a glass ball here, and this is a paper packet. And here, notably, we are grasping this petri dish from inside using the open mode. This last H1 here is the twister mode. Here I have a video to show the picking up process of this ping pong ball and also twisting it. Know that right now it's real time. You can see that we are activating this thing, and then now with bending, and then we're closing on the ping pong ball, and we can pick it up. And next, we're going to activate another set of ligaments, and we're going to be able to generate twisting motion out of it. And this is sped up 4 times because of the material we're using are not that conductive and other issues. We have efforts improving on this, as I shown earlier in the figures, but I don't have time to detail this today. Okay. So those are good, but we identify common drawbacks, actually, all this approach, including my own work. We see that the multi-finger grippers, they are good at manipulating objects smaller than their own sizes, but they typically suffer at manipulating thin, flat, and small objects. If you design a big gripper, it's hard to pick small things, and those multi-finger thing is hard to pick out, let's say, a credit card from the table. For tunable adhesion approach, the tuning is either static, right, by my colleague at Payne, or there are many constraints in picking and releasing. Lightweight objects are particularly hard to release. Sometimes you can pick it up, but you cannot release it. It's more hard to release those objects. So our goal here on robotic manipulation is to design soft end effectors that can be actively tuned, can manipulate objects larger and smaller than their own sizes, towards the ultimate goal of universal manipulation. And we achieve this by proposing novel designs of soft grippers, integrating new understanding of adhesion mechanics. So next, we're going to look at the first example that we use this subsurface stiffness modulation approach to achieve tunable adhesion for manipulation. This actually is based on the previous work by my colleague. We look at this structure, we say, okay, this is good. You insert rigid core, you can get enhanced dry adhesion. But that's it. You cannot change it within a second. Once you fabricate structure, adhesion increase, but you cannot decrease anymore. But what about a small material as the core instead of a rigid material that cannot respond to anything? We can have the small material initially is rigid, such that you can have high adhesion at the beginning, You can pick up objects, you can manipulate them, and then when you want to release, you turn the switch, you soften the material, within a couple seconds, the object will be released. That will be useful, I would see. And the small material that I mentioned earlier, this CPBE, conductive propylene-based elastomer, right, are perfect candidates for the core. For demonstration purpose, okay? We went on to eliminate this. Essentially, we are trying to switch between these two states. When the small material is softened, you're going to have a soft post. When the small material is not softened, you have a rigid core, right? So you can switch between the two when you do the activation of the small core or not. We're able to show that actually, if we play the parameters right, using 40 volts, we're able to get like a 16-17% of the original strains. Here's the percentage of the original strains here. And here there's a T over L ratio, which we keep the L constant. L is the dimension of the gripper. And this T here is the distance from the bottom of the small material to the interface. You can see that when the TL is really small, we are able to achieve 6 times of adhesion change using tens of volts. And this demonstrates the concept, right? The concept is good. So here is a video to show that. You can see this U-shaped thing there. You cannot see the PDMS shell because PDMS is transparent. You can see that we use 80 volts, and this object actually dropped within 1 second in the video, but we sped up the video by 5 times, so that's roughly 4-5 seconds. That's good, but then we ask the question, when we use the material or core, right, most of the material is not contributing, seems like, right? You have this big U-shaped core here, but we know that everything is happening on the interface. Then why don't we kind of modify the design such that, we only keep the material close to the interface? That way, supposedly, we don't have to wait 5 seconds. And supposedly, we don't need tens of volts, right? If you have another material that's more conductive. We went on to implement this idea. We're actually using this aluminum alloy. Then, because it's aluminum alloy, we need to create enough resistance because it's highly conductive, right? We actually use the same layer here, and within this layer, we are trying to do these patterns to make sure the channels are long enough such that we have tangible resistance. And then there's also other advantages, but there are also potential issues because we use this material that can melt later during activation, and that can be troublesome sometimes. There's robotics issue. But anyway, we went on to implement the idea. Here's a video to show that actually this indeed works. This one, we are trying to pick up aluminum disc here with a glass attached on top. You can see that actually we can pick it up, this roughly 1 pound aluminum disc, and we can release it on demand within 1 second using 5 volts. This is a huge improvement compared with previous design. What I didn't show you here is the stiffness tuning is actually not as good as before. The stiffness tuning here we get is roughly 2 times compared with 6 times earlier. The reason for that, we realized actually after we did a careful mechanics analysis, we realized that actually the backing layer actually is useful. It's not completely useless. The thickness or the height of that backing layer is critical actually to make sure you can get enough tunability, but also make sure you can reduce the material, right? Don't get extra material there. That's not contributing. That's very good, and we are happy with that. So the next approach I'm going to talk about is based on subsurface pressure modulation. So we demonstrate this subsurface stiffness modulation, right? We understand that actually the reason why we have tunable adhesion is that we're using small material between soft state and rigid state to change the stress distribution on the interface. And the question we ask is, why can't we use pressure to change the stress distribution on the interface? So we went on to implement the idea. We can have a chamber here. This is a homogeneous material, but it contains a chamber here, an annular chamber, right? We can inflate this chamber, and supposedly the stress distribution on this interface will be changed, and we can also do dropping when we change the stress distribution there. Here is some fabrication, which I'm going to skip the detail about. I think you guys are probably all very familiar with this. This is 3D printing, molding and casting, etc. I'm going to skip that. We also did this finite element analysis using linear superposition principle. We look at the data weight applied by the object we're trying to manipulate. We also look at the pressure applied on the side wall and the pressure on the top and bottom wall. So as you can see from here, this is normalized. So normalized by this one is F divided by A, and then this is the stress distribution normalized by the P here. This one is also stress distribution along normalized by the pressure applied. We can see that actually, among these all three components, this pressure on the sidewall actually is having the largest singularity. We're having 6 times over average value there, where this one 2 times, and this one actually goes negative pressure sometimes. So we realize actually this one can be dominant when pressure is high. That is indeed the case actually. Here you can see when we change the pressure from 0, which is this one here, to 0.1, 0.3, 0.5, 1, this is calibrated by the dead weight applied. We can see that there's this singularity, stress singularity on the edge will actually be suppressed as you increase the pressure. Whereas this one, this singularity here is going to go up. That explains perfectly why initially when we increase the pressure, we're going to see actually a bump up in the dry adhesion strength of the device. By the way, here this sigma is the strength of the device, and sigma 0 is the strength of the device when you don't play with pressure, you keep at atmospheric pressure. And then this one is the pressure applied, normalized once again by the adhesion strength of the device when you don't play with pressure, okay? So then by this setting, then we always start with 1, because when pressure is 0, you're going to have sigma 0 divided by sigma 0, you're going to start with 1. But when you increase the pressure a little bit, you're going to have increase of adhesion because of this suppression of singularity on the edge. And then later on, that got dropped sharply because of this spiking on the sidewall, right, in this region. That explains very nicely why we are seeing this sharp decrease. And we were able to achieve roughly 4 times dry adhesion change with 50 kilopascal pressure input. This is 4 times comes from, if you draw a line from here, like 0.25, you roughly go to this one equal to 1. And this indeed is P divided by sigma 0, where sigma 0 is, the strength of surface pairs, right, against different materials. On glass, on silicon, on aluminum, on polished aluminum. You can see that from this data, all of these numbers roughly 50 kilopascal. So we can use roughly 50 kilopascal here to get 4 times dry adhesion change. That's good. Compared with suction cups, right? We typically use like 100 kilopascal. You create a vacuum there. So from this previous analysis, we realized actually, seems like the major event actually is bending of the sidewall of the soft hollow chamber. Then we ask the question, why not we get simpler and just use directly soft hollow pillars, right? Early on we have the middle post there, and we have an annulus chamber. Why don't we just have a hollow chamber with some sidewall, and that's it? In this case, supposedly we can inflate the structure or deflate the structure. We can all change the stress distribution here, and we can release objects on demand, right? When we implement the idea, and we did experiments, here is we're monitoring the surface contact, the interface contact actually, evolution during the process. And we were able to show that actually using positive pressure and negative pressure, we can both get this initial increase and a sharp drop in the adhesion strength of the device. And this time, actually, is much better than before. Early on, we had 50 kilopascal input. We were getting 4 times dry adhesion change. This time, we're looking at 15 kilopascal in the positive case, and also minus 8 kilopascal in the negative pressure case. We can almost bring down this adhesion strength to 0. We're getting tens of, or even 100 times of adhesion change using even lower pressure, okay? This is much better design than before. And here we're carefully looking at the reason why we're getting those increased or decreased adhesion. We look at the positive pressure case, and we look at the stress distribution along the interface. We can see that actually when you gradually increase the pressure, there will be a bump coming up here, which explains why we are seeing some internal failure here instead of right from the edge. And when you go to 18 kilopascal, literally, even from final simulation, you're going to see the crack initiate some region close to the edge, but not on the edge. That's because here you have a bump you have the highest stress here, and that's why it's failure initiates from there. The negative pressure case is even more interesting. In that, actually, when you do minus 4, right, you don't see much happening. Actually, the adhesion actually goes up a little bit. If you go to minus 8, you can see that actually the sidewall of the soft hollow pillar buckles. This dramatically changed the strain and on the interface, the stress on the interface, and makes this tunable adhesion even more dramatic. We were able to simulate this whole process using finite element simulation, but also we were able to track the surface contact evolution using the camera system we built up earlier. We also did some theoretical analysis to try to understand what is going on, right? What governs the mechanics of this? We see, we can treat this as a bonded shell structure, and then we can see that actually, depending on the geometry and also the material property, we can design this Z parameter here that actually, if you do this dimensionless number here, you can decide actually whether the soft pillar is going to buckle in this we call it mode 2 buckling, or this mode 3 buckling. Mode 2, literally, you have two opposite surface buckling toward each other, whereas mode 3, you're going to have three buckling surfaces. They're 120 degrees apart. Actually, we are able to show that actually, indeed, this analysis is clear when we have this, it's going to do mode 2, and then when we have this parameter, we're going to do mode 3. And mode 2 and mode 3 are important because the corresponding critical pressure actually will be determined by that. And we care about the pressure because we want to keep it low such that it can consume less energy. It can also respond faster. Here is to put our work on the map. These are all previous studies, including our own work. You can see that previous study, they use relative higher pressure, whereas we use something close to 0. And in the meantime, we are having over 100 times dry interchange using this low pressure. And this is much better. And this one actually is indeed the work done by Dr. Guangchao Wan, who graduated here, as I mentioned at the beginning. So here I have some videos to show that actually you can use a micro pump. This is untethered. A micro pump, this hand actually can be replaced with a robotic arm. Then you can pick up this LED light there. This one is, you can also do this, fabricate this array of soft pillars. And you can pick up array of objects selectively. And this one, we're showing that actually we can do this SU pattern. You can pick up those things and then deposit it. Then you can see this SU pattern here. This is real time, by the way. This is real time, and now we can, because we have low pressure, actually we can do, we're talking about on the order of milliseconds, 100 milliseconds. That's good. I'm going to move to the next slide. I believe I have a better demo actually. Here, my student actually tried to pack everything into a pen-like device. This is like a literally pen-like device, and we have this controller here. You can turn, there's a micro pump, and you have a battery here. You can have your soft pillar here. And we demonstrate that actually we can pick up, manipulate this microelectronics part provided by a company that we're working together with. And then we can see that actually you can release it very quickly. The next will be a video about this. This video is really short. It's real time. So this is concurrent, simultaneous plate actually. So I'm going to do it again because it's really short. You can see that actually we press the button here, immediately drops. This is real time. We're not speeding up, and we look at the video and we calculate the time is 120 milliseconds. This is ready to be adopted in the industry, I would say, in terms of response time. Think about all those manipulations, repetitive manipulations. But there are also other issues I'm going to talk about later. What's the distance, what's the gap between being adopted right now and also the version we have right now. Okay, with that, I'm going to do a quick summary of compliant robotic graping that I have covered so far. So my group have been working on this multi-finger soft graper that can do picking up, release, also twisting. We also look at this tunable adhesion-based soft graper that can do pick and place operation using smart materials. We also have a variant version of this. Instead of this big U-shaped core, we have a thin layer. We demonstrate some performance metrics have improved, whereas others suffer a little bit. And this one is a pneumatics-based approach, and we have a better approach when we use this completely soft, completely hollow pillar, right? We're able to do this work. And we are excited for this work, and we are proud of this, but we want to see that actually there are many more open questions in compliant robotic manipulation. So next, I'm going to literally look at this, talk about the outlook and also future work for compliant manipulation with example, actually, about shell adhesion mechanics. So this is the first one, right? This is the fundamental mechanics thing. So we're actually trying to look at the soft hollow pillar structure and ask the question, how can we further improve the performance of it, right? What is the, for example, what's the cap effect? For those gecko-inspired dry adhesive, they have micropillars with cap. And those can significantly increase the adhesion strength. Here we wonder, if we add a cap, what's going to happen? It's going to increase the adhesion strength, but what's its effect on the tunability, right? Also, we look at the cross-section effect. We also look at what if my side wall actually of the chamber is not homogeneous? It has some small material, for example, right? We also look at the potential, for the bottom surface, if I have a bistable structure, what does that mean for the tunability and for pressure needed, etc. These are actually these are proposed in my ASF career proposal. Actually, as Jifeng mentioned, is gonna hopefully it will come through in a couple of weeks. I also try to we have been working on this NRI grant, try to integrate this both SSM approach and also SPM approach to existing robotic grippers for universal gripping. This one, our collaborators at CMU and also Payne, they were able to do some demonstrations. Another thing is application in space. The space is a very unique environment because it features with microgravity, with extreme temperature swings. There's also no air. Actually, this subsurface stiffness modulation will be perfectly matched for this application. The pressure modulation will suffer a little bit because you cannot create negative pressure there inside subsurface because there's no air. Outside is empty, there's nothing. But you can indeed send a pulse of pressure to the chamber using a gas tank. So the SPM approach will work half of the mechanism, I would say, but it can work all the time, but it's based on only the half of the spectrum of the thing we have talked about earlier. I'm trying to explore that, in a NASA proposal. And then also for this ICOR project I did earlier, I mentioned earlier, back in 2018, I was visiting Silicon Valley and other startup companies. So we have been trying to learn from companies, to find out what exactly is the technical pain point they're experiencing in terms of the manipulation. The lesson I learned after doing over 100 customer interview, is that actually the automotive company, right, for example, in Detroit area, they are shifting away from compressed air and vacuum cups due to energy cost considerations. Those compressed air we have in the lab actually is not free, and they have to keep it all the time. And it's not free, and it's some bill that they have to pay regularly, right? So they want to shift away from that. And also, small, delicate, and curved objects have always been challenging to manipulate for all industries. I demonstrated actually manipulation of flat and thin objects. We can do this LED light, which has some curvature, but we have not get to that stage that we are very comfortable with curved objects. We are working on that, but we are not there yet. So these are for future work. So some good points I want to see here is that both the SSM approach and the SPM approaches, they actually consume much less energy, as adhesion is needed only for releasing. The device actually starts with a high adhesion state, which you can pick up objects, you can do manipulation with a robotic arm. Only when you want to release, you either turn the switch to run current through it, or you turn the switch to let the pneumatics go through, right? So you can save a lot of energy in that regard. And but there are challenges. Minimization is challenging because we are talking about some composite structure or some hollow structure with some chamber inside, right? And we want to do small things, and these are challenging. And we are currently pursuing this in an ongoing PFI project, working with a company called Cobham Advanced Electronic Solutions, and also Nose. Nose actually is a company that work on this acoustic units for iPhones that you guys use. I'm pretty sure you guys have many of you have iPhones, and actually they have Nose parts inside. So now these are the examples that Case actually is working with. They work on those chips for defense and for NASA applications. These are typically not that high volume, right? For Apple, you would have many pieces, and you're going to do this is like a literally high volume production or manufacturing. But for these, they're high mix and low volume. It's hard to optimize this because the price is higher. You have to pay attention to the cost. So as an example for the future work, we also look at actually shell adhesion for potential manipulation applications. So here, my colleague here, KT1 at Northeastern, many years ago, more than a decade ago, guys, right? 2011 actually. So they studied this theoretical work. They argue that actually when you have a thin shell, spherical shell, this critical pulling force, which is an indicator of the adhesion strength, will be depending on a lot of things, including the thickness here. You can see the thickness actually here shows up on the denominator here, which means you have a thinner shell, you're going to have higher adhesion. Whereas for the GKR solid sphere case, you don't have those in the equation at all. You just have this surface energy of the material, and then you have pi, you have r, those are geometry, right? You don't have modulus, you don't have thickness there. So this literally says you get thinner, you're going to get higher adhesion. But no one has done experiments to validate the work. And we imagine that actually this spherical shell can potentially be used for compliant manipulation. For example, manipulation of biological samples that's on the smaller scale, like a single cell, which is also a curvature, but then you can put a very small thin shell, right, to pick it up and then hopefully using pressure or some other mechanism to release it, right? So we want to understand actually this mechanics, and we're working on this hyperelastic hemispherical shell with finite thickness, not very thin, but finite thickness, and then involves large deformation. Without going into too much details, these are experiments we're trying to do. We have 3D printed molds. We're trying to pour this anchored PDMS, and turns out actually if you pour anchored PDMS, eventually there will be only a thin layer left on this sphere here. You're able to make those thin shells with elegant accuracy, actually. We then did experiments. We see that actually when T over R is thickness, right, over the radius, when it's very large, you approach the GKR model as expected. Because when T over R equal to 1, that's 10 to the power 0, right? That's 1. And literally you have a half solid sphere. You're going to have this GKR thing there. But when you reduce the thickness, you're going to deviate from this, and eventually you're going to come back a little bit. This is a region that actually predicted by my colleague, KT1. This is the essential region. By the way, this is a log. This is not linear. This is log, okay? So, but when you further decrease the thickness, it doesn't go up as always as that model predicts. Because that model made a lot of assumptions. Eventually, those assumptions are going to break down when the shell is very thin. So we can see that actually, eventually, adhesion come back later, which makes sense actually. We hope that actually this will help the design of soft grippers based on hollow shells. With that, I'm going to conclude. I introduced this interdisciplinary research theme in smart, hybrid, active, and nature-inspired materials, mechanics, and machines for my group. And we do this for better human-machine environment interactions. And we also look at compliant robotic manipulation approaches, integrating smart materials and solid mechanics. These include the multi-finger soft gripper, and also include this pressure modulation, and also include this stiffness modulation, right, for tunable adhesion. We also look at the outlook and future work for robotic manipulation. As a case in point, we look at shell adhesion mechanics. And this is actually currently ongoing research for potential application in compliant manipulation. Once again, I want to revisit the same here. We do a lot of things, seems like we do a lot of things, but actually we focus on materials with tunable stiffness, and we focus on relevant mechanics when we try to design all sorts of robotic mechanisms. I hope I convinced you that we're doing that through the projects that have been detailed today. Last but not least, I want to acknowledge my colleagues and also the funding support for my work. This includes my collaborator, Karen Turner and Payne. We have started working starting 2017. It's been 6 years now, I would see. We're having a lot of projects together and papers together. Another one is my postdoc advisor, Kamal Majidi at CMU. So he has been, he's one of the collaborators on this NRI grant together, and he also literally brought me into this area of soft robotics. Also, KT1, as I mentioned, is shell adhesion work, and Professor Teng Zhang for the soft pillar work that I presented earlier. Last but not least, it's the funding source. So I've been very lucky to have NSF supports on the projects I presented, but also I want to recognize the University of Nevada, Reno, and also Syracuse University for the support of my work. And also I want to say, acknowledge the industrial partners. This include CASE, as I mentioned earlier, and also 3M. I'm trying to, right now I'm sending a PhD student actually to do an intern at 3M. Last but not least, this Aerospace system is a SU startup. Actually, we are working together for this NASA proposal I mentioned earlier. With that, I'm going to thank you for your attention, and I'll be happy to take any questions that you have. Thank you.